Okay, everyone, welcome to today's webinar, Design of Cold Form Steel Buildings in RISA. My name is Ben Follett, and I'm just going to do a bit of an intro, a little bit of housekeeping before I turn things over to my colleague, Debbie Penko, for the majority of the technical content. The first thing I wanted to mention is that if you're having trouble logging into the audio, you can log into the audio via the phone or via your computer audio. Either is fine, so you might just have a phone number that you can dial into. Also, there is a chat box that's in the bottom middle kind of your screen. And so you can expand that chat box to ask questions. I will be monitoring that chat. I'll be monitoring that chat if you have any issues with the webinar. If you have any questions, I would invite you to use the actual Q&A. That will allow everybody to kind of see those questions and will allow our team to answer those questions for the group so that people can see and then kind of go back through those answered questions if they have anything. So it's just a better way to answer those questions. We also are recording the webinar. So we'll be recording the webinar, and the recording of that will be posted on our YouTube channel probably in the next few days, maybe early next week, just because of the Christmas holiday. And then finally, the PDHs. You'll receive the PDHs hopefully in the next few days after we get everything logged into our system, and we'll automatically generate you a PDH for this particular course. And so with that, I'm going to go ahead and turn things over to my colleague, Debbie Penko, for the technical presentation. Deb?
Hi, everybody. Thanks for joining me today. My name is Debbie Penko, and I'll be talking through the design of cold form steel buildings in RISA. My background is actually in cold form steel. Before I worked with RISA, I have done some design of cold form steel, trusses actually. So this is a topic I know well, but it's something I'm excited to bring to RISA, and we'll talk more and more about walls in particular. So cold form steel has been part of RISA for a while, long before I got here, but what we did add in this latest version is wall design. So we'll be focusing on that in particular. So let me jump in. We have a lot to talk about, so I want to show you guys all of what's going to be. Let's see here. Let me see if and of course let's see if I can get the dials here. Okay. So what we want to talk about is going to be a lot of things. In particular, cold form steel wall design has a lot of design assumptions. So we're going to talk a little bit more code than I usually do in this type of presentation. I'd rather focus the software and show you how it works and all that. But I also want to make sure we talk the background of how it got implemented in the program, and specifically some of the design assumptions we're making and things that are going to make a difference in what your results you get. So it's really important to think through that as an engineer, understand exactly what you're getting. So we'll walk through that a little bit. We'll also talk through just a single RISA, 3D single wall component. It's really important to know before you go into a full building, understanding just a single wall, exactly what we're doing in there, and then jumping to a full building. And that will be what we finish off with, RISAFloor and RISA 3D working together for a full cold form steel building design. So we'll have a good amount of stuff to talk through here. And I want to first start out with some of the design code information. So we've had cold form steel in the program. We have a long list of cold form steel in there, AISI S100, and you'll see we have 16, but we go back several years. So it's been long-standing studs and different shapes, and even proprietary shapes are in there. So we have a lot of different cold form steel members. But what was added was the walls. So in particular, there's two codes that actually balance that walls. And so the first code being the S240, that's going to be year 2015, and that's going to be just a general structural framing. And in there's some wall provisions. And then another code, S400, is actually going to go specific to seismic design. As I dug into the codes, this is something that was interesting, is that there's a lot of overlap. So it is one of those ones where you look at it and think, well, I think this is similar. So you're kind of looking for the differences. And seismic gets a little bit more stringent, I think, in my mind when I was looking through it, but mostly very similar. But we'll see kind of different paths and how we designate that. There's definitely paths that are going to be one code versus the other. And we try to do a little bit of that work for you so that you just check both at the same time. So we'll kind of see how that works in the program. So the first thing off for a cold form steel wall, what we're talking about is gravity design and what we're checking for gravity design. So gravity design is pretty easy, right? You can look it up in a table, open up any of these codes and just say, 12 studs at on center would work, right? But mostly when we're talking about gravity design, we're trying to work towards a larger building, also checking shear on that. So we want to make sure the gravity works, and then we also want to jump into the more complexity of the lateral. So we're doing a check on that gravity stud here. You can see you can drop the stud information right on there. So you tell the program you can use what kind of studs you want. We have a variety, everything in our database, and I'll show you that when we open up the program here. But everything in our database is eligible to go as a stud if it makes sense, obviously. So C shapes, CS, whatever you're looking for to be a stud, you can put in there, and you can put the spacing in as well. And we're going to check gravity only load combinations for you. So for gravity, we're not trying to run all the lateral through those repetitive studs. We're trying to just check the gravity. And the way we check that is we're going to look for the envelope load combination. So looking for the worst case gravity combinations we can find. And then we're taking that region and understanding what's happening in that region. And we'll talk a little bit more about regions here in just a second. But each region is checked for the total gravity load coming through. And then we check it against two code bodies. So the S100, which is your standard member check. Then we're also checking this against the wall stud design provisions in the S240. So that case, we've selected the all steel design methodology to do that, which means that we assume it's all structurally sheathing is going to be ignored. And so the unbraced length for the buckling of the stud is going to be taken as the full wall height. And you can see that as we did the design. So these pieces are all based on a member design rule, a wall design rule. And you'll notice at the top here, it says cold form steel wall panel parameters, and this is our design rule. So we put a design rule on a wall, and then we make this assumption, all these different top plate, sill plate studs, and header for the entire wall. And then these elements get checked. So the studs are going to be checked, the top plate, sill plate, and header size. We're putting it in there for self-weight, but it's not going to be actually designed as of yet. So we're using a segmented design, and that means that those areas, the above and below openings, are going to be ineffective, but we're going to be putting in them for self-weight. So studs are checked, full height studs, and the other ones there are going to be for self-weight. So as we talk about this even farther, let's talk a little bit more about what kind of design you can do in the program. So first, the design methodologies this is for lateral. Now we're talking lateral beyond gravity. So for lateral design, there's a lot of design methodologies that you can use from those code references I just mentioned. There's first one off the bat I'll just start with is wood structural sheathing. So you can apply wood structural sheathing, and there's some tables that you can find inside of the codes. So you can dig into either of those codes. They're very similar, as I mentioned, and you can find this similar table. Actually, this is right off. You just Google those. You'll find that the codes actually have this right on available to the public, so you can download this and take a look. But what's specifically about this, when you're looking at this code table, it's a little bit I would say restrictive in a different way than I've seen in wood. We also do wood design for walls, but there's very strict rules on what you can and cannot do in cold form steel walls. And in particular, the one big thing that stands out is the aspect ratio. So we have some maximum aspect ratios listed right there for the type of material you're using, and then you get different parameters for how many fasteners you're using. And the other piece of restriction is that you have a certain designated thickness stud track or blocking in that as well. So if you want to use a 15-30 seconds, you have to be in a 43rd mil thickness. If you try to use a 33, it's not going to work. If you try to use an aspect ratio that exceeds that maximum, it's not going to work. So what I suggest, since it is very narrow in what you're allowed to do in your ratios and in your sizes and things, I suggest opening up the code and understanding what you want to do, what you want to pick before you get down the path of even designing your wall. So look at the code, just say, okay, I'm roughly going to have about this ratio, and start working from there, so you know what's going to work for you. The program will do this for you. Definitely will check whether some of this is going to work for you, and then we do our best to give you some messaging on that. But you'll want to basically have a little bit of education of what you think will work before you jump in. Otherwise, you might keep hitting the wall of, hey, how come my aspect ratio doesn't work? And that would be because, you know, possibly it never meets that max. It always increases over that maximum, something like that. So I just give this as an example, but all of the codes have this. Every single code has a reference that I'm about to show you here has the same level of restrictions in different ways. So for steel sheathing, we have both methods. The actual nice part is we do implement both the table method, and this is another method we also have is the effective width method. And you can see that in chapter E2.3. So that one is the only one that's outside of tables, but the rest of them are all table based. So you can see, and I'll dive into this a little further once we open the program. It's nice inside of RISA, we can see some of these parameters that I'm just showing and how it affects RISA. So you can see exactly what we're looking at there. We also have the gypsum board panels, and that is specific for the S240. That doesn't allow you to do seismic. So you'll notice the S400 is the seismic specific. So that is just for S240. So you're not getting that S400 on that one. And then the fiberboard also is S240. So you have some different materials that you can use, and we have different databases of each one of these materials. So as I open the program here, in the next couple of slides, I'll show you guys how that works. Beyond that, let's talk about the methodology and how it's applied. So we use the type 1 segmented design, and that means that you have, this is similar to wood. It's segmented is how we've always thought of it in wood. And it's very similar. I think this is a common picture for both materials in that you are worried about full height regions so that you have a region that's going the whole span, and it's going to neglect door openings or window openings. And in this case, you could have probably put one in the middle, but it's just going to the outsides. So the two sides of the wall are regions, and on each side of the region is a hold down. And so that is your full region of design, and there's a chord on each side of that region. So each region has chord, it has paneling that's going to resist the lateral, and that we're going to calculate what kind of paneling is going to work to try to resist that. So you have, this is your segmented type design. In how RISA applies that internally, we do a FEA plate mesh. So what we do about this region is that we talk about that region has a certain stiffness based on the panel that's selected. And then we put the chords there as well. So you're going to get like as you apply that shear, that V, you get a tension and compression force in those chords, and then the panel resists it. And basically each region is independently moving. So the force is distributed across there, and the lateral force is going to be based on the relative stiffness of the sheathing. So it's not going to be the length of the wall. It's just based on the stiffness of the sheathing internally. And then the ineffective sections right above and below those openings sort of just don't count, right? There's no stiffness there. So they sort of almost, and we can sometimes see that when we watch a deflected shape of a wall, that area sort of doesn't, it just is there to transfer, but it has not very much stiffness. When we're talking shear walls, this is a good point to mention too, is that this is also very similar to wood for RISA, and we talk about in-plane shear. That's what I'm looking at in this picture, not out-of-plane shear. So this is meant to be part of the lateral resisting system, and it's in there for in-plane, which is in the page if we're looking at it and thinking about how that V is applied, not out of the page, not like we're blowing wind into my computer screen, if that makes sense. So there's very little stiffness in the other direction. Enough stiffness so that it holds the wall up and it doesn't flop over, but it is it's not very stiff in that direction. So that's kind of a thought for how you're thinking about how this shear wall works. So let me keep going here. So on each region, there is a chord force, and a chord chord force is there to distribute tension and compression. As you are pushing on it sideways, in this picture I have shown, you get tension on one side and compression on the other side. And then obviously the wind is going to blow the other way, or the earthquake is going to push the other way, and then it goes in the other direction. So you tell the program in your design rules, if you're your wall, what kind of hold down chord you want to use. This is assumption is that you're going to put a hold down right underneath those chords. Some assumptions too for those chords, you're applying a tension and compression force on this, and this also, the way we calculate that is we think about compression force there. We have a moment over the length of that wall. We also add in, for compression, we add in a tributary area of just one stud, as if it's going to be, resisting just a one stud is going to be in the compression block of that chord. And then for tension, we kind of use a little bit more of the entire wall as if it's holding it down. So it's going to see a moment over the length of that wall plus the axial, P is axial divided by 2, which basically is half the wall is going to be holding it down. So it's a little bit more load helping it to hold it down in tension, if that makes sense. So you've got the ability to change your hold down chord. In that piece right there, you, like I mentioned, just like studs, you can put any type of cord you want in there. You can use back to back, you can use tubes, however you need to get that so that the cord holds down as you needed for capacity. And we'll see that in the results. So hold downs are something that the program is going to give you the force. So in the hold down here, we can see that we assume that the edge of the wall is going to be the center line of the chord. We are recognize that may not be exactly where the hold down is. So you can adjust your hold down with eccentricity, giving it ability to push it basically in based on if you had a back-to-back chord, a tube shape that is, actually a tube would probably be okay, but you can give it a little bit of eccentricity using some calculations there to figure out where your moment is and then push it back from that point. And if you want to add that eccentricity to get that hold down force scooted over a bit, you could do that. The other thing about hold downs, since we don't know what your hold down is going to be, hold downs are actually used in the calculation of the deflection. So hold downs have slip, and that's part of the hand calc, the 4-part hand calc calculation for cold form steel walls for deflection. So you can add a little bit of additional hold down deflection that you'd want to add into the wall, and that will help you there. And I'll talk a little bit about deflection, but deflection is a complex topic because we do it in 2 different methods. We do it in a 4-part calculation, like a hand calc methodology, and that's right out of the code, or we also do it in FEA. So when you're in a larger, bigger structure, like we're going to see at the end of this presentation, you'll see that a bigger model, you want to know the deflection overall, not just the deflection of one single wall. So a hand calc method falls apart when you're trying to do a 3-dimensional large building. So FEA, using the plate methodology, helps there, and we can actually show you the difference between what the plate's FEA deflection is versus what the hand calc method is, and you can use some adjusters to either stiffen up the wall. Typically it's reverse that, make it a little bit more soft so that you get more deflection like the hand calc represents. So I'll show you that in the results when we get there. The bigger piece here, last before we jump into how the program works, is the geometric restriction. So there's a lot of geometric restrictions for these walls to use these tables. There's so many that it became a little difficult to restrain you in that way. So the program is going to we're going to put it back onto you to make sure you're fitting these design and detailing restrictions, right? So a lot of this is detailing type things where you need to make sure that you're following what the code has allowed you to do with member types and member grades and a lot of things. RISA is very customizable, which is great, but it means you can tell us things that we may not know whether you're going down this path of exactly this detailing information. So it's important to open up the book, open up the code references, and just make sure that you are following the ins and outs of what they want prescribed for these table-based information. And you'll see a lot of this references here. There's a lot to look through. So I recommend jumping into that. But what I want to show you first of all is just a RISA 3D, a single wall, and how that works in RISA 3D. We're going to apply gravity and lateral loads, and I'm going to jump into RISA 3D here. See if I can jump in. Okay. Let me grab my mouse and see if I can get there. Okay. So this is a RISA 3D model. I'm looking at just I already drew it just to save us some time since we have a lot to talk about in here, and I put some loads on it. I put some lateral loads. I put some dead loads on it. Really, that's it. Very simple model, but I think one of the things that we have a lot to talk about is as we look through these design rules. So I showed you a little bit of here, but every wall, if I click on this wall, every wall has a design rule with it. So it's a design rule right now, it's set to typical. If you open up the wall design rules, you can actually open it up several ways. You can look at it in a dialogue, which is kind of fun to review it like this. So you can see exactly what you're looking at in here. This tells us the studs. Right now I'm using S16254. If I click on that, it'll show me all the studs I'm allowed to use. This is coming out of the SSMA database, so I can use single, back-to-back, toe-to-toe, whatever I'm looking to do that as a stud. And I can change to any type of material. I have a lot of databases in here, so I could switch between other databases. I can add to this database whatever you're interested in getting that stud shape there, you can. You can also do top plates, sill plates, like we said, header sizes. But the bigger piece here is that chord size right there. So there were certain restrictions on those chords, and that would be something I would pay attention to. So the chord is the edges of that region. And like we showed earlier, and there's going to be a hold down attached to that. So sometimes we need to have a certain minimum of that chord. So 33 is probably small for some of those minimums, but you can increase that, or you can see how it goes if you get design on that. So let me just pop into, I'm going to make it a little bit larger here. So I'll take a 43 and see if that helps us. You can change your spacings for your fasteners. You can narrow that down, let the program size it a bit. You can narrow or increase the thickness design here. So program's going to try to find a good database of sheathing there for you. So you have all of these abilities to do it. And I'm going to just pop into the same exact, I just showed it to you from there. You can see the same thing from a spreadsheet. So it's two different ways in, the same information, however you like to see it. And if you're in the spreadsheet, you can come in here, you'll see the same type of thing. So right now we only offer type 1 segmented, so that's the only way you can get in there. But if you want to do different types of sheathing materials, you just drop that down and you can pick from that. So for the wood one, if you pop over into the schedule, let's open up the schedule, because this is where we get to see a little bit more of that information. So the tables in the code come alive in here in RISA, and this explains a little bit about what we're looking at in the table. And the naming convention is just going to be, if we're looking at a wood sheathing method here, we have 5/32 is the thickness of that wood sheathing. We have S1, structural 1, or OSB, pretty self-explanatory on the type of sheathing that we're talking through. 6/12, okay, that was going to be your fasteners, and we saw that in the tables earlier. And then 43, that's the minimum mill thickness that we're allowed to use from those chords. So we're trying to kind of decode it based on the tables with the names. Excuse me. So the one other piece we did is we added a wording called tall. And what does that mean? Well, that means that you are required up to a 4:1 aspect ratio. So it's going up to be tall. So that's and we have that listed here. So you'll see anything that doesn't say tall doesn't let you up to 4:1 aspect ratio. Another one is, so you have two sets of values for if you're earthquake or not earthquake. So if it's governed by earthquake over here, then we have an EQ listed on that, and then you'll get an actual value based on that. So there is an interesting collection of things from these tables. So we wanted to try to give you the ability to check everything that's needed. And then there are algorithms inside the program to say, is this earthquake? Okay, yes. Then I will check for the ones that have EQ. And then I will also check if the aspect ratio is big, and trying to find the right panel for you if you can find it. So that's why we do a lot of that for you inside the program, but I'm sure you can trick it in different ways with very tall or very beyond a 4:1 ratio or things like that. So it is always good, or maybe you potentially are just going too low or too high in your mill thickness. So some of them are very specific. That's another piece. Let's see if I have an example of that. I think these ones that actually call out, they have to be. There's some ones that force you to be at that thickness. So it's not just an optional minimum, it's an actual must be. So that's something that's to look out for. So you can see the sheathing material is listed here. 4:1 says yes or no. Can you get up to 4:1? If it's not, it's going to be a 2:1. That's kind of how the code reads there. Sheet thickness, fastener spacings, blocking is required, minimum member thickness, and then we walk down the path of, and I mentioned here, the earthquake. The last two columns are your most important columns. What is the shear capacity? That's a very important one for us. So kips per foot. Okay, good, got it. And then shear modulus. So that's going to be your stiffness. So these values are all table-based. They're right here. They're actually outside of the program in an XML format. You can gain access to that as well. There's a lot here, so I do say if you do want to get access to the XML, take a look, use the same formatting we have used so that the program understands what you've entered in there, and we have that listed in the help file too, so you can see that. But it is something you can put your own values in there and create your own database. So let me pop out into here. They're all the same, really, mostly just the same type of thing. You're going into steel, and then you get to see the very similar database, just, different terminology. We're now talking about a steel sheet versus a wood. So few different things, but mostly we're all in the same kind of categories that we're fitting into. So let me pop back over to wood, and we can see gypsum. These are smaller databases, FYI. Just the tables are much more limited, so not much to choose from when you're talking gypsum or when you're talking about fiberboard. But the same idea. So I'm going to pop back over to wood, and we can see here, so we'll be using a table-based options here, and you can tell the program the thickness, minimum and maximum. This is just wide open, really. And then fasteners that you want to use. If you wanted to say, I want to do a minimum of 2 inches up to 6, but I'm just going to leave it at 6 and 6. And then the chord, you can adjust that chord there to be whatever you wanted it to be. So let's give it a 54 or something bigger. And I'm going to go ahead and solve this model. So with all of that in place, really, that's kind of your standard just check through. Before let me show you what I'm running here. I created the load combinations, and I have a variety of different load combinations. I'm going to go ahead and just solve this model. So I'll just solve a batch and an envelope. And this is just running through dead loads, live load. I only have dead load and lateral on this model, so it's pretty basic. But it is important to understand what you get from there. So first of all, you look at your wall panel design, and you can take a look at what came across in the cold form steel axial load. So we break it into axial and in plane. So when I open up the axial first, I see that stud was checked at 12-inch spacing, very low axial check. That's a unity check of very low. And the load combination 1 was governing for that. So we only ran that axial under that gravity load combination, which is the first load combination, which is just a dead load. So that was only gravity. Beyond that, we then checked the chords and all that based on the lateral one. So this is load combination 7. We can also visually see that load combination 7. Let's turn on our loads for a second. I'm going to turn on load combination, and I'm going to go over here to 7. Okay, so we're pushing this direction, and this happens to be the governing one for us for that chord. So again, also very low code check, but so we're not having a problem with that. I'm going to go over to the cold form steel in plane, and in here I can see I get OSB selected. My minimum was a 33, so it would have been fine. My shear check and shear force are listed there, and then the hold down force and hold down a governing location for that load combination for these. Excuse me. Let me look at the detail report, because I think that gives us a lot more information. So I click on the detail report, and I see in here that I have information on what I'm looking at in this load combination. So, or this design. So this design shows me a breakdown of the input. What was done here, all the stud design method was all steel. We had mentioned that. It's a table-based method. It tells me the one big thing I always take away from is this was just a single wall. We could have added openings to it. And I will show you when we get to RISAFloor, an opening, a model with openings. But in this case, it's just a single wall, and it's got a max height to width ratio, which is your aspect ratio of 1.0. And that's important. That number right there is what tells you whether where in the table it goes, if is it too tall, is the ratio too large, things like that. So I always look for this number to understand a little bit more. That gives us all the information for the chords. And then I'm going to go ahead and go open up the controlling region, which is a single region right here, but it tells us what the governing load combination was and what was required and available. It tells us the chords with the tension. And since I pushed on this in both ways, so I'm seeing tension on one side and tension on the other side. It's doing 2 load combinations from each direction, and they're both wind. So this makes a difference because some of those are earthquake designed. So we would have seen an E listed here if this was governing by an earthquake versus if it's governing by wind. So it's something where you want to pay attention to. If you think, I actually think if you are running a model of any size, you want to know what is governing. Is it earthquake or wind? Because that's really going to help you make an actual understanding of why this is being selected, why other ones aren't, and going down that path. So I'm assuming as you go down design, you're going to want to make sure you know if there's a better one selected, or if you understand that earthquake versus wind, that's the first step. As I mentioned, there's 2 types of deflection. So in this model, this is the hand calc method. We're seeing this is going to be 0.029 inches of deflection. That's substantially larger than our finite element deflection. We have a shear stiffness adjustment, so we could soften this wall so that this number gets closer to this number. In the simple wall, I wouldn't really care about it because I'd probably just think about it in this manner. But as I mentioned, when we get to a bigger model, it might make more sense. So I'll show you that here in a second, where you can adjust that. And then as you look more about details of, okay, what happened in this region? You can open up your region report, and inside of this gives you a more breakdown of what happened. This is the axial force in that wall. This is the shear diagram and the moment diagram. This gives us a full breakdown of how all the different pieces that came to be for this calculation. To find that, we also get a little bit more of a breakdown of that panel. Not too much more. It just gives us a breakdown of what the panel thickness was and shear capacity. We get chord design, so it tells us what the chords are going to be and what their calculation are, and stud design, so a calculation of that stud. Deflection is pretty basic here. Just a couple lines exactly repeating what we had already seen up there in the general and the summary. This diagram shows us a little bit of information. I actually love this diagram. It's general. It's not customized because we didn't do that, but we just did a single stud on the end. But what is nice about this, why it's helpful, is because it kind of puts the load combinations listed like this. So the chord forces are spelled out, tension on one side, tension on the other side. This is a different load combination, so I can think through which load combinations push from each side, what the hold down forces were. It gives us a little bit of information on that. So just a good representation. This shows also what stud we were doing for the chord, and then gives us a little call out there. So I like this as just a general, just to understand a bit more. Sometimes it helps me tell the story in my head, how the tension compression forces were working. So the wall panel, design here, it's listed in the node reactions. You can see that you get, just a wall panel max and min. This is showing us the load combinations that govern for this one. You can find specifics. I was showing wall panel design, but you also can show wall panel forces. It tells us what the forces are in that wall. Super easy to see, just max axial, what the load combination was. You're looking at envelope of everything, right? So sometimes that's not helpful. Sometimes you really want to know load combination 7. If you click on the batch, you'll jump into the same spreadsheets and you'll see it's listed per each load combination, which might be more helpful. So when I'm looking at load combination 7, that's what happened on that load combination. and I can see a little bit more information. Now, I mentioned the stiffness can be adjusted. So I want to just show that before we leave this wall panel here. So if I look into this wall, I have just the general information about this wall. It has a material set. You can change that material set. That wasn't something I mentioned, but we do also have just some general materials we put inside of this for the cold form steel walls, or for all cold form steel, not just walls. You can change that. You can add to this. This list is definitely not exhaustive. If you decide to add any materials to this and you want to always have them ready for you, you can always push save as default. So you'll always have a longer list. This is just what comes with the defaults of RISA. But if you wanted to adjust the stiffness of this wall, you can do that here. It's this is your stiffness adjuster. Actually, let's see. Yeah, that's your stiffness adjustment. So you can adjust that stiffness. You can even turn walls on and off, active, inactive, things like that. So you have ability to play with that wall, and it's whatever you're looking to do that. For the last piece before we leave this model, I do want to show one other piece. So we assume that this wall, if you double click on it, has a pinned boundary condition at the base of that wall. You can do pinned, you can do fixed, but really that's a consistently solid boundary condition under the wall. And the wall itself, if we're looking at the wall, I'm going to go to the view and just take a look at this wall for a second. And let's look at the results of this wall here. So the view settings of this wall, we can turn on just a quick view, and I'm going to show, hang on, reactions. We can turn on the reactions underneath that wall. And this wall itself has got plate mesh. So we can turn on, I'm going to see if I can get that to show. Okay. I'll turn off my loads for a second, and I'm going to turn off my color code. I'll turn that back on. Let me show you there we go. So you have a plate mesh underneath this. Each one of these walls has a plate mesh, and that plate mesh is that finite element plate mesh. So it's automatically happening for you. You don't have to do anything to get that to happen. The program does it upon solution. Those walls are now broken into smaller plates, and those plates have stiffness. And if you add openings, you'll get plates around those openings. But in doing so, we also, I'm going to turn this off for a sec, and I'm going to show it like this. We also then, at the base of every one of those plates, the corners of plates, you'll get a reaction. So when I'm looking at this in the wall panel, I can see that, we do a summation in those node reactions for you. We take the total force in the Y direction, the total force in the Z direction, whatever it is, and we solve it and just give you a wall panel result. But it's always nice to understand what's happening along the way internally. Those plates are breaking it up into pieces, and we get each one of those corner forces are going to be tied down at those as either a pin or a fixed boundary condition. So it's a nice way to understand exactly this load combination. We're looking at how the forces are distributing along that boundary condition. Okay, so RISA 3D gives you all of this tools to see, and one piece before let's see here, just a last piece there is that wall panel mesh is right here, is being controlled by the settings, the model settings. So right now we're setting it as a 24-inch mesh, which is a great size mesh. You don't need more than that in a simple model like this. Sometimes I would go larger if you had a bigger model, just because it saves time and space, or you might even go smaller if you want to have more granularity. So it depends on what you're looking for. Okay, let's jump back here. And I think we were here. Let's see if we can get, okay. So the next bigger piece is I want to talk about a full building. So RISA, we talked about RISA 3D as a single component, but RISAFloor works together with RISA 3D to do a full building. And that's important that we understand the full building. So RISAFloor does an analysis of the gravity design, and that allows us, we call it RISAFloor, but it's floor by floor, really, that's the name where it comes from, and it's just a full building. So we have to count all the loads down the building in gravity in RISAFloor, and then we take just the lateral system over to RISA 3D. And inside of that, you apply the lateral loads, and RISA 3D, as we make that transition, will calculate all those forces for us. So seismic, wind, all that gets calculated based on the model as it's defined in RISAFloor. And then it gets applied on a diaphragm basis. So each one of the diaphragms, it automatically creates those as either semi-rigid, flexible, or rigid. And you can tell the program what kind of diaphragm you want, and the program will distribute the loads to the model based on that. So I want to take a look at a model and see how we can make this, how we look through this model. This is kind of a larger structure, and it might help us understand a little bit better what we're looking at. So I'm going to close that, and we're going to open up RISAFloor. So hang on a second, I have to search RISAFloor. Okay, so under RISAFloor, I'm going to pop open this model. Okay, so RISAFloor, if you're familiar with it, I'm going to go ahead and go into the full model, and we're just going to resolve it just so we can see here. So RISAFloor, as I mentioned, is a full building model. It's shown, this model in particular is a podium structure. So I dropped a concrete slab floor at the bottom on this model. And then in this concrete floor here level, I'm going to go down to the very base just for a quick perusal of what we're looking at. And we'll turn off all of our, let's see, we'll say none on that, just so we see what's going on. So this is just a concrete podium slab. I dropped a few openings in it. If we're thinking about this, it's just got a couple walls, some columns, and it's meant to really just be, you know, whatever a podium might look like, as we are maybe a residential above, and this is maybe commercial below, but very common type of building where you might drop above it either wood or cold form steel. So above this, I put in cold form steel. So this RISAFloor in particular is a design tool. So when you start a model in RISAFloor, let me show you what you might look like. Is it more likely looks like this. So the program, you tell the program, I want to put in joists that are CS, channels shaped, cold form steel channels, and I want to drop in a wall, and that wall is just a cold form steel wall. We just tell it a little basics on it, the same kind of basic information. It's cold form steel, it's got some studs, and that's really all you get. You don't have to tell the program much more than that. It will then choose a shape based on what you've laid out. So we already have some default area loads on this structure. So if I turn on my area loads for this model, I have some default office loads across the structure. And in the top right corner, you can see my legend here. Office area loads are everywhere. Internally, I have got some public. I'm assuming this is my my elevator. I designed this building, guys. It's I'm not a great architect, but I had a little elevator shaft coming out, and I have a little hallway, and my apartment/hotel rooms are all off that lobby there. So I'm using a repetitive framing across everywhere to do the design of that for those actual joists there, but internally I'm also applying some loads. So RISAFloor will automatically apply your area load. So I'm going to jump in here. I want to take a look at my area load definitions, and I will tell you right here that I have 10 pounds per square foot of dead load and 50 pounds per square foot of live load that's reducible. And then I can take this into RISA 3D for dynamic analysis here for the dynamic loading of 10 pounds of dynamic mass. So you have all of that design done here in RISAFloor. It designs it. I'm going to turn off the load so we can see that better. And I've got different size shaped joists in here in RISAFloor for the repetitive framing. They are blue, and that's the big difference in RISAFloor to RISA 3D. RISAFloor is the gravity design. And so the program designates gravity elements as blue and lateral elements as red. And you'll notice here in the corner, I have called this, all these members are blue. I just drew them in as blue elements because they are just repetitive framing, so I don't need them part of the lateral system. But I'd like to bring these walls over as part of the lateral system. So the lateral system I have laid out is all of my cold form steel walls, and one wall is not. And this is kind of one of those ones where, as the designer, I looked at this wall and I said, this is a really small wall. It's just a quick opening to drop those walls in. So it's too small. I don't need to have these regions shown like that. So what I'm going to do is just call this this gravity. This is the one is only gravity, but the rest are lateral. Gravity and lateral also always, lateral always gets gravity. So it's not like it's not going to get gravity design, but it's not going to go over to RISA 3D for lateral design. I can make some bigger decisions. Maybe all of this hallway area is not lateral and just the exterior, and maybe I don't need to do different things with that. I can make all sorts of other decisions about where the lateral system lies, but let's just assume that all of these walls are lateral, and we'll talk about it when we get to RISA 3D more. RISAFloor designs all of these for me, so I can check, how they've been designed. That we have a nice detail report inside of RISAFloor for these cold form steel joists. So you can see it's designing based on the bending right now. It tells me the shear, deflection, almost always controls, but I do have, these are longer spans, so bending is typically now here controlling for a lot of these. I can see any of that information either on, a detail report, or you can always go into design results and understand what's going on all of your cold form steel, beams or columns as you go down the path there. We just recently added back-to-back CS or channel shapes for cold form steel inside of RISAFloor design too, so you much better for like a column if you needed to. Podium. This is also doing the reinforcement design, so I think I have a few things missing here, but that's okay. For concrete design, you get reinforcement design. You can see that. I can actually just draw in the support line after the fact, and I can kind of just connect the dots here and create some support lines and generate strips for that. And so let's see, I can just create a quick design strip here, and we get reinforcement design for the entire slab already, just missing a one spot here as we go. RISAFloor ES is what allows me to do this piece. So RISAFloor is the beam supported floor, and RISAFloor ES allows me to add this kind of floor in here. So you can get reinforcement design for a concrete slab, just like I'm showing here. You can do column strips, middle strips. It'll break it down into a lot more information and detail for you on those column strips and middle strips, and then you can take a look at that. So I have a two-way slab design here, and I'm picking up the loads from above. If you ever wondered, how this lined up, I always like to see the floors above, and I show kind of what it looks like as it sits on this floor. So this is a structural concrete slab that the rest of the structure is sitting on, and it's carrying the forces right from these walls into the concrete slab and then down to the bottom of the building. So for RISAFloor, it's important, I'm going to turn off that floor level now for a second here. It's important to see, what would you care about in RISAFloor? This, once the gravity design is done in here, you could then take, for example, the wall forces from here into and find your base reactions either from the podium level, which is the very base of the model. You can find all of those base reactions. Or if you decided, hey, I don't want to do a podium slab together, I want to just do them in two separate models, you could take them and find the first, second, and third floor, go all the way to the first floor and find those base reactions and apply them yourself manually onto the structure. So you have the ability to work through either way. I've just decided to put it all together. Makes sense to me to have it all in one model. The other thing I've done in this model before we move into RISA 3D is that I've put in a semi-rigid diaphragm on this podium level, and then I put rigid diaphragms on the levels above. Cold form steel is similar to wood. You can do rigid, you can do flexible, but you can do semi-rigid. There's pluses and minuses to every type of methodology. Rigid and semi-rigid tend to be probably the most common. But we'll see here once we get over to RISA 3D what happens when you get over there for either kind. So let me see, I'm going to go ahead. I've already run the model. So now I'm going to go ahead and use the director button and take this into RISA 3D. So full gravity design has been done, basically. It was just a couple clicks of the buttons, and you can see you get the full gravity design. before we leave one more piece, let's look at that, the wall detail report. So I'm going to pop open a wall here and just see what we have in here. It's just a general region, one region, and it just checks my studs. Are these studs good for gravity? And looks like they are. So we have stud required capacity, and we've provided a lot more than that, double. So we're plenty good. And you can do a region report where you find out the summary of what's happening in there. I did put openings on these walls, kind of made them more interesting. This then with the openings starts to really talk more about that aspect ratio. So I put giant openings in this model. I think one of the things I was thinking was, this is a condo. We're trying to sell nice big bay windows. So what happens with those openings and how does that work? So let's go ahead and go into RISA 3D. Oh, and I also did put the other pieces, I put a door in there. So very similar. You just drop in a door and it's very similar because this would be more my patio side here. So when I go to RISA 3D, it just asks me to save the model, and I will save that model. And it's going to calculate the wind and the seismic for me. So all I have to do in here is just put in some of the parameters. Mostly it's just the wind speed, exposure category. Typically topographic is zeros, but you can change your base elevation. For example, if this podium was part of the basement and the building didn't start until it got to the cold form steel level, you might move your base elevation, because the wind is going to start at the second floor, not the first floor, or the basement level. So, if I wanted to move that up the structure, I could do that. But for my model, I will just say base elevation is blank because it's going all the way to the bottom. And it's now calculating all of those forces. The big number here, right? QH, kips per square foot. It uses the parameters of the building to find out what is going to be that kips per square foot, and then it applies that wind into the building. So it's going to find out what height that floor level is, finds the KZ there and applies that in the width and the length with the CP, and then we turn that all based on windward and leeward and into getting a force in the X and a force in the Z direction. So these are the forces that are going to go right into the diaphragm, and we'll see that here in a second. Depending on what kind of diaphragm you're looking at, it shows you a little bit more about how it gets applied. Rigid diaphragm goes right into the middle, and then we're going to see the podium, the semi-rigid, is going to be applied slightly differently. It's going to be on the edges. So I push OK. Hang on, say OK. Okay, then I go to the seismic, and the seismic does something very similar. You tell the program a little bit more details, so CT doesn't change too often, but R is your big number, right? So that's your question. If you built this as a double stack story building like I did a podium and I did the cold form, I don't get to take advantage of the cold form higher R value. This is going to just be my standard R for my concrete, lower standard ordinary framing. That's what I put in. So 4, you use the minimum of that. So maybe a reason to do 2 different models, get your better R value, but you still have to carry it down below. So I don't know, that's up to you. I plugged and chugged into where I grew up, which was in New York, and it's not very seismic-y. So I don't have a ton of loads in there, but you can see it breaks it down into this. And we can see that it breaks down exactly the values I'm showing here. So it's got the R values are coming through and showing the big pieces, the base shear. I always look at the base shear. However, the base shear is all based on the weight of the structure. So you always want to, when you're looking at this value, take a look at your weight of your structure. RISAFloor does a really cool calculation of all of the loads, self-weight pieces, but you got to make sure you buy off on this weight of the structure. If you do, then all of a sudden your base shear is going to make a lot of sense, because we're just taking a fraction of that weight to find your forces in the X and the Z direction. So that gives you that 97-ish value here, and that's what is going to be the base shear. So I'm going to go ahead and say okay. It applies all that, and then I take this into RISA 3D. So it launches a new session here of RISA 3D, and hopefully y'all can see that. And we're looking, hang on, it's launching as it goes across. We're bringing across all of those red elements. So it's creating all of the cold form steel walls, all of the concrete elements, everything's coming across. Okay, so we've got, let's see if I can, I think I might have, there we go. Okay, so we've got, this is coming across. It says it's going to bring all the results. So RISAFloor is smart in that it knows everything, the geometry that came across, all the shape sizes, everything. If I had brought beams across, it would start with those gravity elements of those beams. Oops. And so now when we look at this structure, this is what we have in RISA 3D. I'm going to show the diaphragms because otherwise it looks a little like we have a hanging building. But the diaphragms show you that it's connected right from there. So you have, this is our semi-rigid diaphragm. I'm going to just show the loads for a second. So all the dead loads came across, all the live loads came across. Those are calculated over there and come across. And super easy, but it's one of the things I always worry about is what should come across. And if it is when I'm building a model, I'm thinking through the elements come across that are contributing in that area. So, what I also added on the base of my model, I just propped this up with, just pinned columns. So they're just along for the ride, but I want the bottom of the base of my model to really be that concrete shear walls that I have. And some of these are riding all the way to the top for my elevator shaft. But mostly the concrete sections here is just going to be that level. And then above that is just each individual panelized wall. The cold form steel is probably more likely panelized like this, where it's a single panel, where a concrete, you can see I used it as a full wall, and that's just kind of monolithically poured, or, I potentially could break that into segments, but internally it doesn't typically matter because you're plating that. So internally there's a plate mesh and it meshes together and nothing really matters there. But I just always think of cold form steel as panelized. So I think of it as floor by floor like that. You can then turn on, I'm going to turn on my wind loads for a second. So in the wind loads, you can see I'm applying a point load in each direction for wind load right into the center of the diaphragm. We also have a semi-rigid wind load. So let me go ahead and get that right there. So you'll see in the semi-rigid diaphragm, we apply it right to the edges as a windward and a leeward. So it's a little different for rigid versus semi-rigid. And that's because we assume it a little bit, you actually have an edge to your diaphragm if you have a semi-rigid. So you know what side is windward and leeward. When you're talking a rigid diaphragm, everything is infinitely rigid across that area. So it's just, there is no one side or the other really, but it's infinitely rigid. So when we apply that load there, it's right into the center of that diaphragm. So it's super easy to visualize as a point load right in there. And I like to see that shown right on the diaphragm, but you can see it as it builds out. So I'm going to run this model. I'm going to say solve. I've created already some load combinations and I've selected I know wind is going to govern for me on this one. So I'm going to go ahead and just run all of the wind ones that have governed for me. And I basically just go ahead and say a batch and an envelope. RISA 3D, like I mentioned, brought across all of those loads, so I don't have to do much except create load combinations. Load combinations were thought through by me because we have a load combination generator that does it for you quick, but you do have different elements. So I have concrete and I have cold form steel, and I've decided to use ASD design of those cold form steel walls, and the concrete obviously is LRFD. So it's two different things happening on that. So you kind of want to make sure you've actually done that in that way. So you have to think through, and I'll show you guys in a second as I pop open the results here, but the load combinations are important to think through which ones you're going to do for when you're doing mixing materials. So it's running through all of the solutions. You'll also notice in our latest versions of RISA 3D, it's multi-core. Makes it a little faster for me. So it's running through all of those cores. So each load combination goes into a separate core and it runs through until it gets a full design on that and comes back through. So it depends on how many cores you have. Hopefully in your home computers, you have more than 4. I do not. I have a smaller computer, but that's okay. It lets me lighter for travel. So Okay, we're almost done. We have a few iterations of what's happening. So the program is iterating. If you'll notice that it's going down, kind of checking each load and going back and back and back. So we want to try to optimize. It is optimizing the wall panels right now. There's a lot of wall panels, right? So there's a lot happening. There's two pieces of that too. There's also concrete wall panels that are happening. So it is optimizing the shear panels that we want to get. It's also optimizing the reinforcement design. So there's one of the things why you might also decide, in my mind, what is the governing load combinations, what is the ones that you want to do, control, and then start to drill down from that once you find that. So we're in a little bit of a circle here. Hold on, I know this one is going to solve relatively quickly. I think I'm on a little bit of a, with the zoom, it slows it down a bit, but let's see here. So we're going to get at the end, hopefully soon, design. And what we're looking for really is what panels were selected here. So let's go ahead and find that. So I'm going to go ahead and say, okay, so first off, this is a warning log, so not an error, but just warnings. And it gives us a lot of different panels that did not meet the height to width ratio. So I have decisions to make on that. Why either I ignore them, so no problem. The program did ignore it. So it just warns me, hey, you did not meet some kind of design criteria that was set forth. And so what do you want to do with that? I can ignore it, or I can go back into RISAFloor and call it not lateral. These don't count anyway. So maybe I call this just a gravity design. So I could go one by one and try to and just take them out of the design. And that totally would be fine. Either way, really, it's one of the decisions you have to make as a designer. But I find the bigger piece here we want to know is like what happened in that design. So we open up our wall panel design, and we have concrete design. That one was the bigger piece in the lower levels. So we're going to find reinforcement in the concrete level. We have a concrete reinforcement spreadsheet too. But conform steel, I also then have a selection of axial. It's checking the chords, checking axial. So there's a few members that were not done, that aren't meeting code check for my axial check. And I would want to go down that list and say, okay, we better size these up. So do I size them up? It's up to me how I decided to size that up. And let me show you here in a second after we look at our in plane. So I'm going to look at my in plane, and I have something similar where I have I've selected a few different types of walls, and some of them are not quite passing. So what do we do on that? We can do some couple things. We can first identify those. I'm just going to pick out the ones that I want to look at. So I'm just going to right click and say show in the current, and it's going to start to highlight the ones that are failing for me. So I'm going to show selected, scroll down and find a few others. And I might start to look at those in particular. Are their regions really tight and too much for what I'm doing here, or I can delete the regions that I don't care about. So I could actually go into a wall panel and say, just delete R4. I don't need it. I have R1 in there. So maybe that's good enough, and it's not going to meet the criteria the code allows there. So I would do something like that, possibly. I'm also noticing as I look at this that it's a certain floor level, right? So I'm going to push the dim lock button, and I'm seeing the ones I just highlighted are all on that first floor. Well, ahead of time, I had already done some work where I looked at this and I had created a typical, and then I already created a first floor because I knew some of these walls are going to be different sizes. And by construction methods, I might want to do a whole floor of one type of material and then the next floor of a different material. So I might start to go down the path of creating more and more wall panels that I want to specify specifically. Actually going in and saying, well, I know for sure that I'm going to want to do, the cold form steel studs are going to be, this is trying to use, typical is using a effective strip, and it's doing steel sheathing. But maybe I want to do all different ones, change my methodology. You obviously want to try to keep it consistent in the building, but you might want to change the actual. And the other piece you can do is you can go in, and I'm going to break the, let's see, that's okay. I was going to say break the solution, but I can go ahead and pick a certain panel. I can go ahead and tell them, I actually just want to try to use this panel. Now, that may not meet all of my ratios, right? Because I might pick one that would be better off, right? So I maybe pick one more universal one and go with that for the entire building, see if that works. You have a lot of different ways you can do that. So I would say if you set one fully up, it's going to break their solution. And then you can say, okay, that specific panel I'm checking for the entire floor level or the entire area, things like that. You can also just jump in and delete a region. So this region is just too tight. So I'll just go ahead and delete that region. And then I don't have a region on this side. So I think I should be able to do that. Yeah, sorry, RISAFloor would allow me to do that. So that's a good topic to bring up. A lot of geometry, a lot of things are going to be controlled by RISAFloor. If you want to change, you're allowed to change some things. Mostly it's going to be based on your design rules. Things that are seismic related or excuse me, lateral related, I'm allowed to change. But geometry, certain major fundamental things in the program, if I wanted to move a wall, if I wanted to change its shape, if I wanted to remove a region, that's something over in RISA 3D. No, excuse me, RISAFloor that I would do. And so geometry-wise, I'd stay in RISAFloor. Okay, I showed you guys a lot. Sorry, I went over by 5 minutes, but I think that hopefully I gave you a good variety of what we're looking at, and let me know if you have any questions. I can stay on here and help answer questions too, but at this point, let us know and reach out to us with any further questions you have at info@risa.com. Thank you so much for your time today.